Good morning everyone, my name is Divagaran. I'm from KK5 and my matrix number is A1575 and 83. The title for our project is Production of Biohydrogen and Polyhydroxybutyrate, also known as PHP, from Kome. Our main product is polyhydroxybutyrate, or also known as PHP. PHP is a product produced by bacteria for their storage material. In industry, polyhydroxybutyrate can be used in the production of biodegradable plastics, so the usage of PHP is in packaging, medicines, and pharmacology. As a side product, we produce biohydrogen. Biohydrogen is a clean source of energy, so the usage of biohydrogen is in fuel source or for metal treating and in also aerospace application. This is the process flow diagram after heat integration. Initially, POME will be fed into a 6 anaerobic reactors in order to produce biohydrogen, carbon dioxide, and volatile fatty acids at 85 degrees Celsius in 1 bar. This process is facilitated by effective microbes. Biohydrogen and carbon dioxide ventilated as a top product to the absorber. At the absorber, MEA will be used to absorb CO2. Then the pure hydrogen at 99% of purity will be ventilated as a top product, and it will be compressed and condensed into a liquid hydrogen. The bottom of the At the bottom of the absorber, we get our MEA and CO2 mixture, and will be transferred into a stripping column which operates at 130 degrees Celsius and 1 bar. Here, carbon dioxide will be vaporized and condensed and compressed into a liquid carbon dioxide. The MEA will be recycled into the absorber column. The water product, which is VFA, or also known as volatile fatty acid and mainly composed of acetic acid, will be channeled into a filter. Here the effective microbes will be filtered out and the rest of the liquid will be transferred into an evaporator to evaporate the water, and then the solution will be concentrated and it will be sent to a second evaporator to evaporate the acetic acids. Here the acetic acid will be used as a feed for the aerobic fermentation. Here the Common species is used to produce PHP. Since the PHP is an intracellular product, a ball mill is used to crush the cells to release the PHP. After the PHP was released, it will be mixed with acetones to make it dissolve in the liquid, and then the solution will be filtered to remove the Common species. After that, the liquid product will be mixed with methanol to make the PHP solid again, and will be centrifuged and the solid will be dried in a dryer, and then we get a almost pure polyhydroxybutyrate.
Assalamualaikum and good afternoon to the lecturers. My name is Nur Sharafina binti Sulaiman, and today I will be presenting and explaining to you about the plan location and layout for our PHB and biohydrogen production. We have surveyed and made evaluations on the three main locations in order to find the best location for our plant. As you can see in the table form, we have Sungai Buloh, Pelabuhan Klang, and Mentakat Pahang. The evaluation consists of all the primary factors that needs to be put into consideration. The location with the highest score will indicate that it is the most suitable location for our plant, and from the evaluation, it can be concluded that Sungai Buloh is our best option. Some of the strong points that prove this location is the best option is that the raw material supply, which is POME, is available only 2 km away from the location, and this is possible through piping, and thus we can eliminate the transportation cost. Other than that, the land price of 19 million with land area of 10.5 acre is very reasonable. So this is the satellite view and the land view. For the plant layout, we will have the main process, which is the anaerobic fermentation outdoor due to its large volume, and the PHP production at the center, followed by its downstream process indoor. And then we will have the hydrogen and carbon dioxide product underground due to its hazardous properties.
The hazardous material that used in the production of Fydp and biohydrogen are acetone, ammonium nitrate, methanol, carbon dioxide, and hydrogen gas. Acetone that might cause irritation, highly flammable liquid and vapor, but it is stable under fire condition. Ammonium nitrate might cause irritation. It is known as strong oxidizing agent. Methanol might cause residual injury, high flammable liquid and vapor, stable under fire condition. The carbon dioxide might cause residual injury. It is non-flammable and stable under normal condition. Hydrogen gas has no health hazard, but it is vaporized easily, will burn readily in air, stable in non-reactive condition.
For the HAZOP analysis in the anaerobic fermenter, there are few nodes. For example, the first node is inside the fermenter. The guide word is low, which is low temperature in fermenter. The cause of low temperature in fermenter is the valve of steam in fails close. The consequences are low conversion. The safeguards are the temperature controller, high temperature alarm, and then action can be taken is scheduled maintenance and inspection. The next guide word is high temperature in fermenter. The cause of this high temperature is valve of steam in fails opened. The consequences are overheating in reactor, product form do not meet specification, which means the purity may vary, increase in pressure caused by overheating. So the safeguard taken as the other temperature controller and low temperature alarm, and the actions are schedule maintenance and inspections.
Now we will be seeing the HAZOP for the absorber column. For the absorber column, we will be focusing on the node inside the absorber, and the parameter we will be controlling will be pressure. We will be controlling pressure in the absorber because if the absorber has a very high pressure or very low pressure, it will not be able to separate the CO2 and MEA efficiently. What's used to control pressure is low pressure controller, low pressure alarm, pressure relief valve, and high pressure alarm. The actions that would be taken to control pressure is scheduled inspection and maintenance and installation of emergency shutdown system.
This is the HAZOP analysis for dryer. Analysis is done inside the rotary dryer. The parameter involved is temperature. For low temperature in dryer, the cause will be the valve of steam in fill close. It might cause low efficiency of separation or no separation occur. Safeguard to this is temperature controller and low temperature alarm. Action can be done is to schedule inspection and maintenance. For high temperature in dryer, the cause will be the valve of steam in fill open. It might cause overheating in dryer and increase in pressure. The safeguard assisting are temperature controller and high temperature alarm. The action can be done include schedule inspection and maintenance and install emergency shutdown system.
The HAZOP analysis for evaporator is pressure, which is inside the evaporator. So the guide word is low and high. The deviation for low is low pressure inside the evaporator, high pressure in the inside the evaporator. The low pressure can cause failure of control valve, low flow of the product, while the high pressure will overflow of the product. Then the consequences from the failure, the product did not meet the specification, no separation will occur. Then if high pressure, it can cause overheating of the evaporator. So the safeguard is used for the evaporator is low pressure controller, low pressure alarm for low pressure, then high pressure relief valve for high pressure, and high pressure alarm. So the action needed to be used for the HAZOP is schedule and inspection of maintenance, housekeeping, and schedule cleaning regularly.
The HAZOP for seed fermenter will be focused more on the inside part of the fermenter because that is the most crucial part that needs to be assessed. The parameter is level and the guide word used is less and more. Deviation could either be low level of glucose or high level of glucose in the seed fermenter. Some of the causes that leads to low level of glucose are if the inlet pipe 85 are partially blocked or leaked, the inlet valve failed close, or the valve have leakage. The consequences are less product will be formed as there is no sufficient amount of glucose sent to the main fermenters to produce the product, while the causes that could lead to the high level of glucose is if the inlet valve fail open and overflows the glucose in the seed fermenter, where spillage and loss of containment can occur. Thus, the safeguards we can have are low and high level alarm and a level control. We will also have scheduled inspection and regular maintenance.
Next, we will be seeing the waste treatment of our plant. As we can see, we have three types of waste: solid waste, wastewater, and gas waste. Solid waste will be exiting stream 96, wastewater will be exiting stream 101, and gas waste will be exiting stream 89. Our plant complies to certain acts and regulation. First is Environmental Quality Industrial Effluent Regulation 2009. This act is followed to discharge waste into river according to standard A or standard B. The next act is Environmental Quality or Scheduled Waste Regulations 2005 and Environmental Quality Clean Air Regulations 1978. Shows the COD and BOD value before treatment. The COD value before treatment is 1,014,048.20 milligram per liter, while the BOD value is 270,838.09. While the second table shows the COD and BOD value after treatment in aeration tank. Table shows the COD and BOD value after the treatment in clarifier tank, which is also the final COD and BOD value. The COD value is The final COD value is 97.35 mg per liter, while the final BOD value is 8.76 mg per liter, meeting the standard B of discharge requirement. Waste minimization can be seen in our sludge treatment process, which contains a sludge thickener tank and a sludge dewatering lagoon. These two processes reduces the amount of water contained in the sludge and hence reduces the overall weight of the sludge. This is important since we will be sending our waste to quality alarm twice a week. An excess mass of sludge could only increase the price.
In profitability analysis, there are 6 indicators which indicate whether the project is profitable or not. Firstly, the MAR depends on the type of processes and the level of risk for the project. The MAR value of 25% is chosen as the plant is a new product in Malaysian market to ensure the safe investment as we just start our company. A method that does not consider the time value of money, ROI, PVP, and net return are the indicators. ROI calculated is higher than an RR, so the project is profitable. The payback period of 2.4 years is the total time taken to recover the cost of an investment. The net return of this project is 659,000 ringgit. For method that consider time value of money, MPV and DCFR are the indicator. The MPV is 22.2 million ringgit. The project is considered profitable. Meanwhile, the DCFR of 29% is higher than MARR. The project is safe, attractive to invest. We will move on into mechanical and detailed design of main equipments. Aerobic fermenter carries out main accumulation of polyhydroxy butyrate where aerobic fermentation occurs in this fermenter. The process will take place at 35 degrees Celsius and a pressure of 1.3 bar at pH of 5.7 for 24 hours continuously facilitated by Chromomonas species. The excess air and carbon dioxide will be vented as a top product while PHP and biomass will be discharged at bottom product. The continuous stir tank bioreactor is used for efficient mass transfer between medium and microbes. It is chosen because of the simplicity of construction with low operating costs and easy to clean and maintain. This type of fermenter consists of a cylindrical vessel with a motor-driven central shaft that supports impeller. Now will be the detailed design of aerobic fermenter. The type of impeller chosen is flat blade turbine Rushton, also known as flat blade radial turbine for having 4 or more vertical blades equally spaced around a disc. It is usually used in a mixing component with low or medium viscosity. The jacket is designed to cool down the fermenter at a constant temperature of 35 degrees Celsius since the heat is released during the fermentation due to the heat of reaction. The fermentation process in aerobic fermenter is needed to carry out under sterile condition. The medium must be sterilized to ensure the absence of any living organism. The process of sterilization is by heating with direct injection of saturated steam. It is usually performed in a batch mode of 121 degrees Celsius for typically 15 to 30 minutes. The heating will be whole for a short duration and being cooled to 35 degrees Celsius. The aerobic fermenter is designed with a vertical vessel with 2-to-1 ellipsoidal head at the top and the bottom. This column is designed under internal pressure. The construction material is authentic stainless steel type 316L with corrosion allowance of 2 mm. For aerobic fermenter, the thickness of the vessel determined is 8 mm with MAWP vessel of 2.6 bar. After performing stress calculation, both stress analysis and elastic stability are safe. For the support of vessel, conical skirt support is chosen to provide more support to this fermenter. Skirt support is used as this is a vertical vessel. Since the dimension of main aerobic fermenter is big, double plate with gusset base ring is chosen for the support of the aerobic fermenter and make the vessel more stable and strongly built. The type of flange joint is used for connecting pipes are welding net flange. It is suitable for extreme service conditions where the flange is likely to be subjected to temperature, shear, and vibration loads. This is the mechanical drawing for the aerobic fermenter R107.
We will be seeing the mechanical and detailed design of stripping column S101. Stripping column is used to separate carbon dioxide and MEA. Initially, we will have a mixture of carbon dioxide and hydrogen, which we will be separating using MEA. Stripping column is a part of absorption and stripping of gas process. Carbon dioxide and hydrogen is separated using MEA in an absorption column, and in the next column, which is a stripping column, the MEA and carbon dioxide is separated. The separated hydrogen and carbon dioxide is celled, while the separated MEA is recycled back to the absorption column to separate more carbon dioxide and hydrogen. The design temperature of the stripping column is 95 degrees Celsius. The design pressure is 1.1 bar, and it uses an internal pressure procedure of designing the stripping column. The table shows the detailed design summary of the stripping column. The operating pressure is 15 psi, the pressure is 21 psi. The material of construction of the stripping column is austenitic stainless steel type 316L. The vessel height is 39.37 inch. The corrosion allowance is 78.74 inch. The nominal thickness is 1.09 inch. The maximum allowable working pressure of vessel is 637.12 psi. The skirt thickness is 0.016 meter. The type of flange joint is welding neck flanges. The type of vessel support is cylindrical skirt of plain carbon steel. This is the mechanical drawing of the stripping column. The stripping column has 3 inlets and 2 outlets. The inlets are CO2 and MEA mixture, reboiler stream and a reflux stream. The outlets are carbon dioxide and liquid MEA. The type of stripping column used is packed bed stripping column. Though packed bait stripping column is more expensive compared to plate stripping column, we will be using a packed stripping column since it is more resistant towards corrosive materials. MEA is a corrosive material and hence we would need a more corrosive resistant material. The type of packing used inside the stripping column is random packing using ceramic Rashik rings. This type of packing is used since it could really reduce the hold up time of liquid and hence reduce the corrosion inside the column. The mixture of CO2 and MEA enters through a liquid inlet and is distributed into the packing by a liquid distributor. A demister pad is placed close to the outlet of carbon dioxide to remove entrant liquid droplets from gas stream.
Now I will elaborate on the Cattery boiler unit for detailed design and mechanical design. First of all, the function of this Cattery boiler is to generate a flux of vapor where liquid will first flow into the shell where there is a tube bundle, and boiling will take place from the outside of the tube bundle, and the vapor will return back to the stripping column to drive the separation process. From the block diagram, there is one inlet, which is the MEA and carbon dioxide in liquid form, while there are two outlets, which are the top outlet, where MEA and carbon dioxide vapor are sent back to the stripping column for stripping process, while the bottom outlet is where liquid MEA flows out to be recycled. The Cattery boiler is operating at temperature of 120 degrees Celsius and at a pressure of 1.1 bar. And the most commonly used construction material is the carbon steel type WCA, and the length of tube is 4.8 meters. The tube that will be used for this Cattery boiler is the U-tube, and there are 32 number of U-tubes that are arranged in square arrangements with the typical pitch of 37.5 millimeters. While we take the minimum band radius and the tube bundle diameter of 45 mm and 420 mm respectively. The shell diameter is 840 meter and the wear height is 500 mm, which is the retaining wall to always keep the tube bundle covered with liquid. The Cattery boiler are essentially pool boiling devices, and their design is based on data for nucleate boiling. So by using the Mostinsky equation, the nucleate boiling coefficient is 2246 watt per meter squared Celsius. Now for the mechanical design, the design pressure and temperature of this vessel is 120 degrees Celsius and 1.2 bar respectively. The nominal thickness of the vessel is 3 millimeters and the MEWP vessel calculated is 1.7 psi. Steam is used as the service fluid of the Cattery boiler at 1.7 bar at the tube side. For stress calculation, the bending stress for short vessel is negligible, and the primary stress is well below the design maximum allowable stress of 74.46 Newton per millimeter squared. Thus, the pressure vessel can be considered workable. The vessel design is considered safe because the compressive stress is 0.829 Newton per millimeter squared, which is well below the buckling stress. Thus, this is the final drawing of the Cattery boiler with a stationary head type A, a channel, and a removable cover, combined with a shell type K, a kettle type reboiler, and with a rear head type T, which is the pull-through floating head. So I hope this is a clear presentation. Thank you so much for listening.
This is the mechanical design of evaporator E102. The design temperature is 100 degrees Celsius. Design pressure is 1.2 bar. So the procedure needed is internal pressure procedure. So the evaporator E102 is used to evaporate water and acetic from pomade and glucose. So the inlet we have acetic acid, water, pomade and glucose, while the vapor we go out as acetic acid and water. The liquid is pomade and glucose. As we know, the operating temperature is 100 degrees Celsius, operating pressure is 1.2 bar. So the material construction for the shell is carbon steel, while for the tube is stainless steel. So the maximum heat loss is 2646 kilowatt. The length of tube is 1.8, while the number of tubes is 119 tubes. The pitch triangular is 75 millimeter. The vessel height is 3 meter, while the shear diameter is 0.98 or 1 meter. So the amount of steam in is 0.9 meter cube per kilogram. The steam in temperature is 100 degrees Celsius. The pressure of steam in is 1.2 bar, while the amount of steam out is 0.7 meter cube per kilogram. The temperature steam out is 100 degrees Celsius, while the pressure of steam out is 1.1 bar. This is for the mechanical design summary. So the material construction of the tubes, as we know, is stainless steel type 316L. The vessel diameter is 1.0. The vessel height is 3.0 meter. So the shell height of the ellipsoidal head is 24.15 meter. Cylindrical is 28.84 meter, while the ellipsoidal head is 29.06 meter. So the overall minimum thickness is 4 mm. The corrosion allowance for the evaporator is 2. The nominal thickness is 6. So the MAWP vessel is 20.28 psi or equal to 1.4 bar, which is higher than the operating pressure. So the type of vessel support is conical skirt support. So skirt thickness is 8 mm. The actual required is 131. The base ring thickness is 9.33, while the type of flange joint is neck type. So this is the mechanical design for the evaporator. The height of the evaporator is 3 meter. The steam will go in from the downward, then it will go to the upward, and the condensate will go out at C. So the feed will flow down in the tube, and the product liquid will go to the E, and the vapor will go to the B. So this is the top view cross sectional. So we have B flanges, and C as we show it from the upward. So we have here the thickness of the evaporator. So this is the skirt. So we have height of the skirt is 1 meter. The thickness is 50. So this is the tube arrangement. The tube arrangement is in triangular pitch. So the tube will be 50 in the diameter and 60 the outer diameter. So the arrangement is 75 mm. So this is the tube arrangement, as we have here is 119 tubes. So this is the cross sectional of welding neck flanges.
For detailed design, I have designed rotary drum dryer D101. The function of dryer is to dry the solid PHP to a moisture level less than 5%. Before designing the rotary drum dryer, I have made some assumptions, which is constant specific heat capacity, constant heat transfer throughout the drum, moisture content of the feed is constant. The table on the left shows the summary of detailed design of the rotary drum dryer. The total heat required to dry the solid product is 735,384 kJ per hour. By using the total heat transfer, the mass air flow rate is calculated, which is 7,664 kg per hour. By using the air flow rate, the diameter of the drum is calculated to be 1 meter with the volume of 3.45 meter with the length of 4.2 meter. Another important part of the drum is the flight. The function of the flight is to lift and shower the product to ensure the solid completely dries. So the number of flight is 9 with the lip angle of 40 degree and the radial height which is 0.129 meter. For the mechanical design of the rotary drum dryer, the material used is carbon steel SA285 grade C with the design temperature of 343.33 degrees Celsius with the design pressure of 1.7 bar. The thickness of the drum is calculated 22 mm. which gives the outside diameter is 1.02 meters. The speed of the drum also is calculated, which is 6 rpm. The gear set also has been designed for the drum, which, for example, the number of teeth of pinion is 13 and the number of teeth for the gear is 17. The table on the left below summarizes for the gear design. This is the mechanical drawing of the rotary drum dryer. The top figure shows the side view of the rotary drum dryer, which includes shows the stream in and stream out, and then the outside gear. And then the figure below shows the cross-sectional view of the rotary drum dryer, which shows the flight arrangement, the inlet pipe for the solid feed and the air feed, and then the outlet pipe of the solid and the exhaust air. The bottom figure shows the cross-sectional view of the drum, which shows the angle between the flight, which is 40 degrees Celsius, 40 degree, and the figure at the bottom left shows the gear arrangement.